Welcome to Section 7 of Biostatistics. As a review, you can think of biostatistics in three arms: performing the study, evaluating the study, and applying the study clinically. In this lecture, we are still learning to apply the study by focusing on positive predictive values and negative predictive values. So let's get started. Positive predictive values tell you the probability that you will have the disease if you test positive, and positive predictive values will increase with increased prevalence. And you can find positive predictive values by taking the true positive number and dividing that by the true positive plus the false positive number. A better or simpler way to conceptualize this is to view the numerator as those with a positive test result and have the disease. In other words, the true positive group, while the denominator is simply those who have a positive test result, regardless of whether or not they have the disease. So let's quickly draw out our 2x2 table and recall that disease status is along the top and test result is along the side. And true positives are those who test positive and have the disease. And those that test positive but don't have the disease are false positives. And those that test negative and don't have the disease are true negatives. And those that have the disease but test negative are false negatives. And positive predictive value equals the true positives divided by the true positives plus the false positives. Or rather, true positives divided by everyone that had a positive test result. By definition, if you have a positive test, positive predictive value will tell you the probability of actually having the disease. In other words, positive predictive value tells you the probability that you are a true positive. So now let's solidify this information with a question. Let's say there are 350 patients with suspected polymyositis, and they are tested by measuring the serum anti-Jo1 antibodies in their blood. Now there are 100 patients with a negative test, but 50 of them do not have polymyositis. The remaining 250 patients are positive, 150 of which do not have polymyositis. What is the positive predictive value of this test? When you are given a problem like this, it's helpful to quickly sketch out a 2x2 table so you can easily discern the numbers you need. And we are told that 250 patients test positive, so we'll put that number right here to keep track of it. Of those 250, 100 actually have the disease. In other words, those are true positives. So 250 minus 100 is 150. Therefore, we have 150 patients who tested positive but don't have the disease. Now recall that positive predictive value equals true positives divided by true positives plus false positives. Or rather, true positives divided by all who have a positive test result, which is simply 100 divided by 250. And this gives us 0.4 or 40%. In other words, if you have a positive test result, there is a 40% chance you have the disease. Now for negative predictive value. Negative predictive value tells you the probability that you will not have the disease if you test negative. Negative predictive value increases with decreased prevalence. You can mathematically calculate the negative predictive value by taking the true negative number and dividing that by the true negatives plus the false negatives. The alternative way is to look at the numerator as being those who tested negative and don't have the disease. In other words, the true negative group. And the denominator is simply everyone who got a negative test result, regardless of whether or not they have the disease. So let's draw out the 2x2 table. And true negatives are those that test negative and do not have the disease. So this bottom right box. And those who test negative but have the disease are false negatives. And recall that negative predictive value equals the true negatives divided by the true negatives plus the false negatives. Or more simply, the true negatives divided by everyone that had a negative test result. And recall the definition of negative predictive value. If you have a negative test result, negative predictive value will tell you the probability that you do not have the disease. In other words, negative predictive value tells you the probability that you are a true negative. Now let's do a question to solidify this. Let's say the negative predictive value of test A is 80%. 1,000 patients test negative. What number of these patients are false negatives? So let's draw out the 2x2 table and recall that negative predictive value equals the true negatives divided by all who tested negative. In the question stem, we are told that 1,000 patients tested negative. So we will put this number here to keep track of it. And if 1,000 tested negative, this becomes our denominator. Now we are told that the negative predictive value is 80%. So this is the information we were given, and we are asked to find the false negative number, or those that have the disease but test negative anyways. So the first thing that we can do is find the true negative number. And we can do this with the information we were given. After all, negative predictive value, which is 80%, is merely telling us the percentage of our negative test results that are true negatives. Therefore, we can find our true negative number by taking 80% of 1,000, or 0.8 times 1,000. And this gives us 800. So our true negative number is 800, which we will put in this bottom right box. They don't have the disease, and they tested negative. Now the false negative number is simply the difference between 1,000 and 800, and this gives us 200. So what's our false negative number? It's 200, and this answers the question. Now let's relate positive and negative predictive values to prevalence. Positive predictive value increases as the prevalence increases, while negative predictive value increases when the prevalence decreases. Let's demonstrate the prevalence of disease along the x-axis, and we will represent the negative predictive value along the y-axis on the left, and the positive predictive value along the y-axis on the right. As you can see, as the prevalence increases to the right, the positive predictive value increases. And recall the definition for positive predictive value. If you have a positive test, positive predictive value tells you the probability that you will have the disease. Therefore, it makes sense that if a disease is very common and prevalence increases to the right, as we've demonstrated here, that your positive predictive value will increase. Now let's turn our attention to the left side. Notice that as prevalence decreases, the negative predictive value increases. And recall the definition of negative predictive value. If you get a negative test, the negative predictive value will tell you the probability that you really don't have the disease. Therefore, it makes sense that as a disease becomes very rare or less prevalent, the chances of you not having the disease if you get a negative test result would increase. So now let's do a question to solidify this concept. 2 men undergo a test that screens for malaria. Man A lives in the United States, while man B lives in Southeast Asia. If both men have a negative test result, which one is more likely to be disease-free? So we have man A in the United States and man B in Southeast Asia. Both patients test negative for malaria. So which patient is more likely to be disease-free? What we're talking about here is negative predictive value. Recall the definition for negative predictive value. If you get a negative test result, negative predictive value tells you the probability that you do not have the disease. So this question is basically asking us to compare the negative predictive value between those that test negative in the United States versus those that test negative in Southeast Asia. To get this question correct, you need to assume that malaria is less prevalent in the United States and more prevalent in Southeast Asia. Now recall from the graph that we used earlier that as disease prevalence decreases, the negative predictive value increases. So, in the United States, if the prevalence of malaria is lower, then we would picture the negative predictive value appearing over here, where negative predictive value is higher. Conversely, in Southeast Asia, if prevalence is higher, we would picture the negative predictive value to be lower on this end. So, by definition, the man with a higher negative predictive value is more likely to be disease-free. So in which patient is the negative predictive value higher? It's man A. Therefore, which patient is more likely to be disease-free? It's man A. Now let's relate positive and negative predictive values to sensitivity and specificity. Sometimes this concept can be very confusing, So let's make it perfectly clear. Think of specificity and positive predictive value together, and think of sensitivity and negative predictive value together. So let's first focus on specificity and positive predictive value. Now, specificity is inversely proportional to false positive rate. We learned this from Section 6, when we stated that the false positive rate equals 1 minus the specificity. As specificity goes up, the false positive rate goes down. They are inversely proportional. Lastly, specificity is directly proportional to positive predictive value. Now let's focus on sensitivity and negative predictive value. Sensitivity is inversely proportional to the false negative rate. In this relationship, we learn from Section 6. The false negative rate equals 1 minus the sensitivity. As sensitivity goes up, the false negative rate goes down. And finally, sensitivity is proportional to the negative predictive value. Now, this is a lot of relationships to keep straight. We have specificity, sensitivity, positive predictive values, negative predictive values, false positive rates, false negative rates. To keep all of these straight, it can be very difficult. However, this mnemonic can keep everything straight and make it very simple for you. Positive specs are falsely positive. Again, positive specs are falsely positive. Now, don't take this sentence literally. Just use it to help you remember that positive predictive value is proportional to the specificity, which are related to the false positive rate, which of course we recognize is an inverse relationship. If you can keep these three elements straight, positive predictive value, specificity, and the false positive rate, you will know that by default, the negative predictive value is associated with sensitivity and inversely related to the false negative rate. Again, just remember this mnemonic. Positive specs are falsely positive. Now let's clarify the relationship of specificity and the positive predictive value. So let's draw out our 2x2 table. Recall those that do not have the disease but still test positive are false positives. This box. Now looking at the graph, a very specific test would be here. So none of these disease-free patients tested positive. They all tested negative. So this test, with a cutoff here, with positives being to the right and negatives to the left, would indicate high specificity. And since none of our diseased patients showed up positive, we have a very low false positive rate, which in this case is 0. And recall the definition for positive predictive value. If you have a positive test result, positive predictive value tells you the probability that you will have the disease. So in this test, with 100% specificity, if you have a positive test result, then the positive predictive value indicates that you will have the disease. After all, you'll be one of these guys, and the only patients that fall above this cutoff line are diseased patients. So in summary, the specificity is proportional to the positive predictive value and inversely proportional to the false positive rate. And we've demonstrated this here. If specificity is high, positive predictive value will be high, and your false positive rate will be low. On the other hand, if you have a very sensitive test, you're catching all of these diseased patients, which means the number of these who have the disease and test negative is very low. So we'd picture the cutoff being somewhere in here. Your false negative rate is low, indicating you're catching all of your diseased patients. So this test is very sensitive, indicating that the false negative rate is low. Now recall the definition for negative predictive value. If you get a negative test result, negative predictive value will give you the probability of not having the disease. And as you can see, with this cutoff value, everything above this line would be a positive test, and everything below this line would be a negative test. And this test is very sensitive, so if you get a negative test result, you will be one of these people, which are the people who don't have the disease. So your negative predictive value is very high in a sensitive test. And recall the mnemonic, positive specs are falsely positive. This reminds us that positive predictive value is proportional to specificity and inversely proportional to false positives. So by default, we know that negative predictive value is proportional to the sensitivity and inversely proportional to the false negative rate. And we've demonstrated this relationship here. High sensitivity indicates a low false negative rate and a high negative predictive value. So now let's do a question to solidify this knowledge. Let's say an ongoing research study is evaluating a diagnostic test. Early in the study, at time A, a preliminary calculation finds the specificity to be 90%. The study continues, and re-examination of the data 2 years later, at time B, finds that the specificity has decreased. What happened to the positive predictive value and the false positive rate from time A to time B? So we are given 2 times, time A and time B. We are told that the specificity at time A is 90%. But after more data was available at time B, the specificity had decreased. And we are asked to determine what happened to the false positive rate and the positive predictive value from time A to time B. To get this question right, quickly remember the mnemonic. Positive specs are falsely positive. This reminds us that the positive predictive value is proportional to the specificity and inversely proportional to the false positive rate. So if from time A to time B, the specificity decreased, then the false positive rate must have gone up and the positive predictive value must have gone down, which answers our question. And that concludes this section.